So today we are going to learn adiabatic chain. What is an adiabatic chain? If the change of pressure and volume of a gas takes place under such a condition that no heat enters or leaves the gas. Very important. The change of pressure and volume of a gas takes place under such a condition that no heat enters or leaves the gas. Understood? Which means that Q is constant. Q is constant. So, if we go by first law of thermodynamics, Q was equal to U2 minus U1 plus work done plus W. Now Q has become 0. Q is equal to 0. So, U2 minus, sorry, U2 minus U1 is equal to minus W, which means that external work, in order to do external work, the internal energy of the gas is being used, right? The internal energy of the gas is being used to do external work. Okay, so and you must also know that as Q is 0, molar specific heat in an adiabatic process is 0. As Q is 0, molar specific heat in an adiabatic process is 0. The molar specific heat in an isothermal was infinity, and molar specific heat in this adiabatic process, it is 0, right? Now, you must have also learned in the previous class that isothermal change is a very slow process, right? Isothermal process is a very slow process, but adiabatic process is a very quick one. Adiabatic process is a very quick one. Some conditions has to be satisfied, right? So some conditions has to be satisfied for a gas to undergo an adiabatic change, right? Now, for an adiabatic change, the gas must be kept in a container which has a very thick layer of heat insulating material. Very thick layer of heat insulating material. Why? Because no heat should enter the system and no heat should come out of the system, because there is no transfer of heat. The heat content remains same. No heat should go out of the gas, and no heat should enter the gas. Understood? Now, uh, therefore, the process should be performed very quickly so that the changes are brought very rapidly, right? And no change in heat takes place. Adiabatic change is a very quick one, very fast process. Okay. Adiabatic in adiabatic change, the Boyle's law does not hold good, right? The Boyle's law does not hold good. In adiabatic change, the Boyle's law has to be modified as PV to the power gamma. To the power gamma, I am writing y. PV to the power gamma is equals to constant. Not PV is constant, but PV to the power gamma is constant, right? PV to the power gamma is constant. And you know what is gamma? Gamma was Cp by Cv, capital Cp by Cv, the ratio of molar specific heat at constant pressure by molar specific heat at constant volume. Okay, and this is one formula, and other formula for adiabatic change is T V to the power gamma minus 1. V to the power gamma minus 1. Gamma minus 1 is in the power. Okay, gamma minus 1 is the power of V. Better to take the second bracket. Now this is equals to constant, and next is one more, P, relation of P and T. P to the power gamma minus 1 divided by T to the power gamma divided by T to the power gamma. is equal to constant. Okay. So these three formula are valid for adiabatic chain. For isothermal, the formulas where PV is constant, V by T is constant, and P by T is constant. Remember? And now this is for adiabatic chain. Okay. Now, so the next topic is the adiabatics and the isothermals, right? So, the plot of P versus V are mostly known as the adiabatics and the isothermals. And if you see this, that the slope of isothermal, uh, the slope of isothermal is uh, more more than the slope of adiabatics. Means adiabatics are more steeper than isothermals. Adiabatics are more steeper than isothermals. And the formula can be derived that dP by dV is equal to minus P by V. Okay, this is for isothermal. Since PV is constant, this is for isothermal, the slope of an isothermal. This is slope of isothermal, slope of isothermals, right? dP by dV is equal to minus P by V. But in case of adiabatics, PV to the power gamma was constant, right? PV to the power gamma was constant, right? So PV to the power gamma was constant. So if we differentiate this, then dP by dV will be equal to minus gamma P by V, which means that the slope of adiabatic is gamma times more than the slope of isothermal. This is slope of adiabatic. So we can write slope of adiabatic is gamma times the slope of isothermal. So adiabatics are more steeper than isothermals. Okay. So our next topic for discussion is work done in an adiabatic process. Now let us consider n moles of an ideal gas. We have n moles of an ideal gas and it undergoes an adiabatic expansion, so that the initial values of final pressure, volume and temperature are P1, V1 and T1 are the initial pressure, volume and temperature, and P2, V2 and T2 are the final pressure, volume and temperature of that ideal gas which has undergone expansion under adiabatic process. Now we know that P1 V1 is equal to nRT1 and P2 V2 is equal to nRT2. Now U2 minus U1, change in internal energy, is equal to N CV into T2 minus T1. Now W is minus U2 minus U1 in case of an adiabatic change. So N CV T1 minus T2. Now we can write, we have taken CV outside and N T1 minus T2. Instead of N T1 minus T2, we can easily write P1 V1 by R minus P2 V2 by R. And taking R outside, CV by R is CV by R into P2 V2, P1 V1 minus P2 V2. If there is a bracket here, then it would put this. So now CV, and instead of R, what we can write, instead of R I have written CP minus CV. Instead of R I have written CP minus CV, and I have converted P1 V1 minus P2 V2 into NR T1 minus T2. Okay, and now instead of this CV by CP minus CV, we can write gamma minus 1, 1 by gamma minus 1, because CV, if it comes under here, it is CP by CV gamma and minus 1. So the expression for work done is nr T1 minus T2 divided by gamma minus 1. So this is the expression for work done in an adiabatic process.